So, in the last class, we had studied how to get the equation of state for ideal quantum gases, right? So we started from these generating functions. From that, we derived the partition function. From that, we calculated the entropy, and then we defined the temperature and chemical potential of ideal gases from that. And then from that, we were able to derive expressions for the equation of state, the internal energy, and also the average occupation number of a given energy level for ideal quantum gases. And from that, we extended to classical gases as well. And then we derived the Maxwell-Boltzmann equation. And we also calculated the statistics of ideal classical gases as well. Right. So today, in today's session, we will discuss a bit more further about quantum gases. So we will discuss how to calculate the statistics of fermions and bosons at high temperature limit and low temperature limit. And you will see that in the high temperature limit, they look like similar. They are similar to the statistics of classical ideal gas only. But in the low temperature limit, you get to see a very few special characteristics. So fermions have their own special characteristics at low temperatures, and bosons also have their own special characteristics at low temperatures. So these are a few interesting things which one can get by studying quantum gases at low temperatures, and they also have very important physical applications. Okay. So these are a few things which I'm going to cover in today's session, and after that, if I get time, then I will also discuss a few problems on these issues. Okay. So to start with, let us recap a bit of what we had done in the previous class as well. So for a gas of non-interacting quantum particles, which are confined within a box of site L, we had calculated the energy levels, right? And then we had taken the limit L going to infinity. So in the limit of L going to infinity, we initially for a finite L, we had discrete energy levels, right? And then as the limit of L goes to infinity, these energy levels become continuous. So then we replace the summation by an integration. So earlier we had a summation over this logarithmic quantity. And then if we take the limit L going to infinity, we replace that summation by an integration like this. Okay. So this was an expression which we had derived in the previous session only. So beta p is equal to q equal to -1 for fermions, plus 1 for fermions and -1 for bosons, divided by C0 cube integration d3r ln of 1 plus q e to the power minus r square e to the power beta mu. Okay, where r square is equal to beta epsilon j. This is the energy of the level j, and C0 is written in terms of this formula over here. Okay, so C0 can, and this formula can be written in terms of a quantity known as lambda th. So what is lambda th? So lambda th is something which I'm introducing right now in this session, because the quantities which we will derive later, they have a physical meaning, and a lot of them that is related to lambda th. So lambda th is the thermal de Broglie wavelength. Okay, it is defined in this manner, that lambda th is equal to h by root over of 2 pi mkBt, where h is the Planck's constant, m is the mass of the particle, and t is the temperature. Okay, and kb is the Boltzmann constant. So this is known as the thermal de Broglie wavelength. And what is the physical significance of this quantity? Well, if you this has dimensions of length, right? So lambda th cube, it will have dimensions of volume. Now, if I multiply the volume in terms of number density, I get the total number, right? So if I have a quantity like rho into lambda th cube, so that will give me the number of particles which are contained within a volume whose which is defined by the length scale equal to the thermal de Broglie wavelength. Okay. Now, if rho into lambda cube is very large, then what happens is that I have a lot of particles which are confined within that but small volume. So in that limit, the quantum effects become important, right? So if you are to distinguish between when to consider a gas to be a quantum gas or a classical gas, then you need to look at this limit, that is rho into lambda th cube. Okay, so if rho into lambda th cube is of the order of 1 or greater than that, then you need to consider the quantum effects. Okay, so you need to consider a quantum ideal gas. On the other hand, if rho into lambda th cube is much less than 1, then it is in the limit of a classical gas. Basically, the gas is very rarefied in this case, and then the quantum effects are negligible, and then you can make a classical approximation and treat it as a classical gas. Okay, so in terms of lambda th cube, this is the expression for beta p. Okay, and there is one more quantity. which is z, which is equal to e to the power beta mu. This is known as the fugacity of a gas. And this is the quantity which we will be using in our expansions later on. So, since r square can be written in terms of nx square, ny square, and nz square, so in the three axes which are spanned by nx, ny, and nz, because of spherical symmetry of the distribution of the wave numbers of a free particle, we can replace d3r by 4 pi r square dr, okay, due to spherical symmetry. And if we do that, then beta p turns out to be equal to this quantity over here, where you see 4 pi has come out of the integration, and in the integration I have r square ln 1 plus q e to the power minus r squared z, z is this thing, into dr. Now I make the substitution that x is equal to r square, then dx becomes equal to 2r dr, and dr is equal to dx by 2 by root over x. So if I substitute these quantities, then beta p is equal to 2 times cube divided by lambda th cube root over pi integration 0 to infinity x to the power half ln of 1 plus qz e to the power minus x dx. Okay. Now, there is one more thing which you need to consider over here, which we did not consider in the last class. That is the degeneracy of a given energy level. Okay, so what do I mean by degeneracy? So r square is equal to nx square plus ny square plus nz square, right? So suppose that r square is some particular value. For example, it can be any integral integer value, and then you will find that for certain integer values nx, ny, and nz can have different values, but they end up giving the same value of r square. Okay, so we say that that particular energy level is degenerate, and the degeneracy is quantified by the number of combinations of nx, ny, and nz, which end up giving me the same value of r square. So let us suppose for simplicity that each of my energy level is g4 degenerate. That means for every energy level, there are g states which give me the same value of r. Okay, then basically I have to multiply this quantity with g, right? Because if you go back to the expression of entropy which I had earlier, g is basically multiplying the number of microstates. Okay, so that's why I need to multiply this. Sorry, it's raising to the power, so log of that gets multiplied. Okay, so that is why I need to multiply this with the degeneracy factor, and then beta p becomes equal to 2g cube divided by lambda cube into root over pi 0 to infinity integration x to the power half ln of 1 plus qz e to the power minus x. Okay. So similarly, if we consider the number density of the particles which we had earlier, then we had rho is equal to 1 by c0 cube d3r and this expression. Now again, if we use the spherical symmetry of the distribution of the quantum numbers, and also if we say that each level has a g-fold degeneracy, then the expression for rho turns out to be this. That is, rho is equal to 2g divided by lambda cube root over pi integration from 0 to infinity x to the power half divided by e to the power x z to the power minus 1 plus q dx. And similarly, we can do the same thing for the energy per unit volume of the system, internal energy per unit volume. So this was what we had earlier. And then if we use the g-fold degeneracy and the spherical symmetry, we get this expression for beta small u, where small u is a capital U, that is the internal energy, divided by capital V, the volume of the system. So beta small u is equal to 2g by lambda cube root pi integration of 0 to infinity x to the power 3 by 2 divided by e to the power x z power minus 1 plus q into dx. Okay, so you see that there is a similarity between these expressions of rho and beta u. I will come to this a bit later. Before that, let us simplify this expression further for beta p. Okay, so what we do is that we integrate this expression, equation 3, by parts. So first we take the integral of x, and then we take the derivative of log x. Okay, just as you do integration by parts. So this is the term which comes out of the integral for x, and this is the term which comes out of the derivative for log x. So because I took the derivative of log x, I have a factor of 1 plus qz e to the power minus x into the denominator, and the factor of qz e to the power minus x in the numerator. And because of taking the integration over x, I get this factor of x to the power 3 by 2 multiplied by 2 by 3 over here. Now let us look at these two quantities in in more detail. Okay, so if I consider x equal to 0, then this term is equal to 0, right? Because x is sitting outside over here. And if I take the limit x going to infinity, then this term becomes equal to 1, okay? Because this is 0, so 1 plus 0 is 1, and log of 1 is also again equal to 0, right? So in both these limits, this term is equal to 0, so it drops out. And what I have is this thing. So beta p is equal to 4gz divided by 3 lambda cube root pi integration 0 to infinity e to the power minus x to the power 3 by 2 divided by this. So I divide both the numerator and denominator by e to the power minus x, and then I get this thing, that is x to the power 3 by 2 divided by e to the power x z to the power minus 1 plus q, okay, into dx. And if I compare this expression with equation 5 over here, which I got for total energy, then you will see that beta p is nothing but 2 by 3 into u beta. Okay, so in other words, p is equal to 2/3 into u. So this was an expression which we had also derived earlier for this classical ideal gas, right? So for that also the total energy per unit volume turned out to be equal to this thing. Okay, so we have this expression for p over here, right? And this expression for the number density, this also looks similar. Okay, so how do we express them in more simple terms? Well, we define a quantity like this. Okay, so fmq of z is defined as 1 divided by m minus m1 factorial integration from 0 to infinity x to the power m minus 1 divided by e to the power x z minus 1 plus q. Okay, so we define a quantity like this, and we also look at a few integrals, I mean few of the, what do I say, few relations of gamma functions, because these will also be helpful. So you know that m minus 1 factorial can be written as gamma of m, and gamma of half is equal to root pi. Okay, so this fmq of z is nothing but 1 by gamma m integration of this quantity, right? So how does this help us then? So if you look at this expression, you have e to the power x z minus 1 plus q over here and here as well. And in the numerator, you have m minus 1 and 3 by 2. So this basically implies that m should be equal to 5 by 2. So if I put m equal to 5 by 2 over here, I get 3 by 2 here, right? So then I can express beta p in terms of f 5 by 2 superscript qz. So how do I do that? I have an extra factor of 3 by 2 factorial, which comes in my denominator. Now 3 by 2 factorial is gamma 5 by 2, and gamma 5 by 2 is nothing but 3 by 4 root pi. So if I take the 4 over here, then I get 3 by 4 root pi over here. So this is g by lambda cube, gamma 3 by 2, integration from 0 to z, x to the power 3 by 2, e to the power x, z minus 1 plus q. Okay. And this entire thing is nothing but f5 by 2 q of z. Okay, so then I can write beta p as g by lambda cube, f5 by 2 of z, like this. Similarly, for this number density, the expression of rho which I had over here, you will see that I can take the 2 down over here, and you have half over here, right? So this corresponds to m equal to 3 by 2. So for m equal to 3 by 2, gamma 3 by 2 would imply basically half into root pi. So I take the 2 down over here, and what I get is this. So this is basically gamma half integration 0 to infinity x to the power half and this thing. So this is equal to f3 by 2. Okay. So rho is equal to g by lambda cube f3 by 2 q of z. And if I invert this equation, I mean invert this function, then I can calculate z in terms of rho. So z is nothing but f inverse of lambda cube rho by g. Okay. So you see that equation 9, equation 8, and this equation, equation 6. Using these three equations, we can express the pressure, the number density, and the internal energy per unit volume, that is the energy density of a quantum ideal gas, in terms of the fugacity of the gas Z and the temperature via the thermal de Broglie wavelength. Okay, so once we have got these simple expressions, now we can proceed with deriving the high temperature and the low temperature expansions of these quantities, right? So, any questions till now or any doubts? Okay. So if there are no doubts, then I will move ahead with the derivation of these high temperature and low temperature expansions. Okay. So first let us take a look at the high temperature expansion. So as T goes to infinity, this is high temperature limit. Beta is 1 over kBT, so beta goes to 0, right? So if beta goes to 0, what does this mean for F? Okay, so FMQ, we had 1 by m minus 1 factorial 0 to infinity, x to the power minus 1, z e power minus x divided by 1 plus qz e power minus x into dx. So if I compare with the F which I had over here, so what have I done differently here is that, yes, so F was here. So I multiplied the numerator and denominator by e to the power minus x into z. Okay, and then I get this. All right, now let us look at this term z e to the power minus x divided by 1 plus qz e to the power minus x. So if I take this out, then 1 by 1 plus qz e to the power minus x, this is the sum of an infinite GP series whose common ratio is equal to minus qz e to the power minus x. Right. So I can write it in terms of this summation alpha equal to 0 to infinity of this infinite GP series minus qz e to the power minus x raised to the power alpha multiplied by this extra term z e to the power minus x. Okay. So by rearranging the terms, I can write this as a summation alpha equal to 0 to infinity q to the power alpha z power alpha plus 1 e to the power minus alpha plus 1 into x. Okay, minus alpha x minus x like that. Right? So if I substitute this expression into f, then this is what I get. Okay. Now let us see if we can simplify this even more further. We know that q can take values of plus or minus 1, right? For fermions, it's 1 plus 1. For bosons, it's minus 1. So if we consider that thing, then this summation from alpha equal to 0 to infinity can be rewritten in terms of a summation of alpha equal to 1 to infinity. Okay. So if you look at this summation, alpha equal to 1 to infinity minus q alpha plus 1 z power alpha e to the minus alpha x, this is the same as this summation, right? Because here you have z to the power alpha plus 1 because it's going from 0. And instead of that, I have only alpha because it's going from 1. Similarly, instead of alpha plus 1 over here, I have alpha. All right. And instead of alpha over here, I have alpha plus 1 over here. Okay. Alpha plus 1 or alpha minus 1 would not have made any difference because q is only plus 1 or minus 1, right? So this summation can also be written in this manner. Then f and q of z becomes 1 by m minus 1 factorial summation of over alpha, alpha going from 1 to infinity, minus q to the power alpha plus 1, z to the power alpha. Then I put in the integral sign 0 to infinity, e to the power minus alpha x, x to the power m minus 1 into dx. Okay. Now, if you're familiar with gamma functions, you will quickly realize that this integral is nothing but gamma m divided by alpha m. Okay. And gamma m, as we know, is equal to m minus 1 factorial divided by alpha m. Right? So then I can get rid of this integral by this expression itself, and m minus 1 factorial cancels out with this m minus 1 factorial over here. And so then f mq of z becomes equal to summation alpha equal to 1 to infinity minus q to the power alpha plus 1 z to the power alpha divided by alpha to the power of m. Okay, so this is what my expression comes down to. So one thing I forgot to ask was that, are you familiar with gamma functions? So have you seen this integral written in terms of this gamma function previously? Yes. Okay. So gamma function is basically you can express this integral in terms of a function which is known as the gamma function. Okay, in this manner. All right. So once I'm able to express this in terms of gamma functions, then I get this expression for fmqz. So I can expand this summation and write it as fmq of z is equal to z minus qz square by 2 to the power m plus z cube by 3 to the power m, and so on and so forth. So basically, I have expanded this summation over here. All right. So next, what I do is that I use this expression for rho lambda cube by g beta, which I got earlier. Okay. So earlier I saw that rho is equal to g by lambda cube f3 by 2, right? So then rho lambda cube by g is equal to f3 by 2 q of z. All right. So in terms of, instead of m, if I substitute 3 by 2, m equal to 3 by 2, then this is equal to z minus qz squared by 2 to the power 3 by 2 plus z cube by 3 to the power 3 by 2 minus qz to the power 4 by 4 to the power 3 by 2, and so on and so forth. All right. And in doing the summation, I had assumed that q square is equal to 1, which is normal, right? So as t goes to infinity, we know that the thermal de Broglie wavelength lambda was h by square root of 2 pi mkbt. So as t goes to infinity, lambda goes to 0. Right. So if lambda goes to 0, then this left hand side for a finite value of rho is a small quantity. So then this f is also a small quantity. Now if f has to be small, you will see individually all these terms have term by term have to be small. That means we can conclude that for f to be a small quantity, we should have z to be a small quantity as well. All right, that means we have to have z also approaching 0. But z was equal to e to the power beta mu. And beta was going, if beta goes to 0, then e to the power beta mu would go to 1. So then you might ask that how is it that z is going to 0 over here? So the answer is that you actually have the chemical potential, that is mu, becoming a large and negative value at high temperatures. So this is something we will also see in the later sections of our derivations as well. So here you have mu going to large and negative values, and that is how z approaches 0. So now if z is going to 0 and my rho is a finite quantity, then uh, I can express rho in terms of a power series. I can express z as a power series of rho, because rho is also a small quantity in comparison to the temperature, right? So I can write z as C1 rho plus C2 rho square plus C3 rho cube, and so on and so forth. So if I plug this expression of z into this expression over here, then what I get is that rho lambda cube by g is equal to C1 rho plus C2 rho square plus so on. This is the first term. Second term is minus q by 3 by q by 2 to the power 3 by 2 into z square. So q by 2 to the power 3 by 2 into z square, that is C1 rho plus C2 rho square, and so on, plus higher order terms, which are much smaller than these two terms. Why? Because z is very small. Z is going to 0. So higher parts of z will be even smaller. So for the time being, we neglect those higher terms and we make this approximation. Now, since rho is also small, what we do is that we also neglect the terms which have rho cube and higher order. Okay, so we only include terms up to rho and rho square, and we claim that they are the ones which significantly contribute to this left hand side. Okay, so what we have is that if we drop rho cube and higher order terms, then the right hand side is basically C1 into rho plus C2 minus Q C1 square divided by 2 to the power 3 by 2. This thing comes from the second term into rho square, and so on. Next, we equate the coefficients of the same powers on rho on the right hand side and left hand side. So the right hand side has all powers of rho, and the left hand side only has rho to the power 1. Okay, so if we equate the coefficient of rho to the power 1, then we get C1 rho, C1 is equal to lambda cube by g. Okay, if we equate the coefficient of rho square, you will see the coefficient of rho square on the left hand side is equal to 0, right? So C2 minus Q C1 square by 2 to the power 3 by 2 is equal to 0. Or in other words, Q C2 is equal to Q C1 square divided by 2 to the power 3 by 2. and C1 was this thing. So C2 is equal to Q by 2 to the power 3 by 2 lambda cube by G whole square. Okay, so then we can write, go back to this power series form of Z, and then we write Z is equal to lambda cube by G rho plus Q by 2 to the power 3 by 2 lambda cube by G whole square rho square and so on. Okay, so if I take the high temperature limit, that is T going to infinity, then lambda is going to 0. So you see that lambda cube squared, that is lambda to the power 6, is much smaller than lambda cube. So we can neglect this term and we write the fugacity as approximately equal to lambda cube rho by G. Now once simply you can say that the fugacity of this quantum ideal gas, it also approaches 0 in the limit of T going to infinity because lambda is also approaching 0. All right. So once we get this power series expansion of Z, and we also calculate the coefficients C1, C2, and C3, we can plug this into the expression of pressure as well. How? So we had found out that beta P is equal to G by lambda cube F5 by 2 of Z. All right. And what is F5 by 2? F5 by 2 is nothing but if you substitute m equal to 5 by 2 in this expression. So F5 by 2 is Z minus QZ squared by 2 to the power 5 by 2 plus Z cube by 3 to the power 5 by 2 and so on. Okay. So then beta P is equal to G by lambda cube Z minus QZ squared by 2 to the power 5 by 2 plus Z cube by 3 to the power 5 by 2 and so on. Now I replace Z by its power series expansion, that is Z is equal to C1 rho plus C2 rho square and so on. So I replace Z over here, I replace Z in the second term, and I also replace Z in this third term over here. Okay. Now I again take the equal coefficients of rho together, equal powers of rho. So rho to the power 1 term has only lambda cube by G as its coefficient. Rho square term, I can get a rho square term from here and here only. Right. So if I look at this rho square term, its coefficient is C2. And the coefficient of this rho square term is basically minus QC1 square by 2 to the power 5 by 2. So these are the two rows, these are the two coefficients of the two rho square terms multiplied by rho square over here. And then I also look at a higher order, the next higher order term of rho, that is rho cube. So I can get one rho cube from here, that is C3, which I have not calculated. There is one rho cube which comes from here, that is multiplication of rho square with rho. And there is a rho cube term which comes from here. And if I include all these coefficients, I get this thing into rho cube and so on. All right. So then I can get an expansion of pressure in terms of the density in the high temperature limit. So if I expand out these coefficients, I take them outside, lambda cube by G cancels out over here. Beta is equal to KBT. I take rho outside this entire bracket over here. So P is equal to rho KBT multiplied by 1 coming from the first term plus Q by 2 to the power 5 by 2 lambda cube by G into rho plus some other term into lambda cube by G whole square into rho square. Sorry, there won't be a plus sign. This is a multiplication into rho square and so on. Right. So you see that in the limit of T going to infinity, since lambda goes to 0, this term becomes 0 and this term becomes 0, and I'm left with nothing but P is equal to rho kBT. So in the high temperature limit, I recovered the ideal classical gas equation of state from quantum gas as well. So in the high temperature limit, both the Bose gas and the Fermi gas, they both behave identically, and both of them approach the classical ideal gas as seen before. Okay, so this concludes our discussion on the high temperature limit. After this, I will move on to the more interesting section on the low temperature expansion. So before I go into the low temperature expansion, are there any questions or doubts? Or is there any portion which I need to repeat?
No, sir.
Okay, so if there are no doubts, then let's look at the low temperature expansion now. So first, I will take a look at Fermi gases. We know that the for the Fermi Dirac distribution, the average occupation number That is the number of fermions in the energy level epsilon j is given by nj, which is equal to 1 divided by e to the power beta into epsilon j minus mu plus 1. This is the well-known Fermi-Dirac distribution which we had derived in the last class. Now let us look at what happens as t goes to 0. As t goes to 0, you will find that beta goes to 0, right? So if as t goes to 0, beta will go to infinity. This is a misprint over here. Beta should go to infinity because beta is 1 by kbt. So if beta goes to infinity, then this term becomes very large. And e to the power a large quantity is even larger, right? So e to the power this quantity becomes very large. Now, there are two ways in which this can become large. How? One is that if epsilon j is greater than mu, then this is positive. So e to the power beta multiplied by a positive quantity, and this entire thing becomes a large positive quantity. So this basically becomes infinity. So 1 divided by infinity is equal to 0. So nj becomes equal to 0 if epsilon j is greater than mu or if mu is less than epsilon j. All right. And what happens if it's the other way around? If mu is greater than epsilon j, then this is negative, right? So a negative quantity multiplied by a large quantity in total gives me a very large negative quantity. So this approaches minus infinity as a t goes to 0. And e to the power minus
सर हिंदी
infinity
में
is,
पढ़ाइए।
yes,
हिंदी में पढ़ाइए।
हिंदी में पढ़ाएंगे आपको।
हाँ
इंग्लिश में थोड़ा तकलीफ हो रहा है।
हाँ हाँ।
ओके, बट देर इज ऑल्सो समबडी एल्स। तो
ओ,
एनीवे, तो मैं दोनों भाषाओं में बोलता हूँ। तो
ओके
आई विल स्पीक इन बोथ हिंदी एंड इंग्लिश इफ दैट्स ओके।
ओके
ओके ना? ठीक है।
ओके।
ओके, सो व्हाट हैपेंस व्हेन बीटा गोज टू इन्फिनिटी? मतलब कि क्या होता है अगर मैं बीटा को इनफाइनाइट ले लूँ? ठीक है। सो इफ बीटा गोज टू इन्फिनिटी, दिस क्वांटिटी बिकम्स अ वेरी लार्ज क्वांटिटी। ये क्वांटिटी बहुत बड़ा हो जाता है। ठीक है। So, if epsilon j is greater than mu, then this is a large positive quantity. मतलब कि अगर epsilon j mu से ज़्यादा है, तो ये बड़ा positive quantity बन जाता है. And then this is like e to the power plus infinity, and 1 by infinity is equal to 0, right? So that is why nj is equal to 0. तो basically ये 1 by infinity हो जाता है और वो that is equal to 0, इसीलिए nj 0 होता है. All right. And if mu is less than epsilon, greater than epsilon j, okay, अगर mu epsilon j से बड़ा हो, तो then this quantity epsilon j minus mu, this is negative, right? And so then if beta goes to infinity, then this is equal to minus infinity. So ये एक बड़ा negative quantity बन जाता है. And then e to the power of minus infinity is equal to 0, right? So that is why this is 1 by 0 plus 1, which is equal to 1. So that is why nj is equal to 1 when mu is greater than epsilon j. All right. So if I consider both of them and then I draw a graph of nj versus epsilon j, तो मैं यहाँ एक ग्राफ प्लॉट कर रहा हूँ जिधर epsilon j is on the x-axis, nj is on the y-axis. All right. So you would see that at a particular value of epsilon j, that is epsilon j equal to mu, when epsilon j is greater than this value, this nj is equal to 0. Or when epsilon j is less than this value, then nj is equal to 1. Okay. तो अगर epsilon j mu से बड़ा होगा ये 0 है, mu से छोटा है तो ये 1 है. So what is the speciality about mu equal to epsilon j? This is known as the Fermi energy level. So what happens is that at t equal to 0, all the energy levels starting from j equal to 0 up to epsilon f, these are fully occupied, while all the other levels with epsilon j greater than epsilon f are completely empty. मतलब कि सारे के सारे जो एनर्जी लेवल्स है अप टू द फर्मी एनर्जी लेवल ऑफ एप्सिलॉन एफ, सारे के सारे फुल्ली ऑक्यूपाइड होता है एट टी इक्वल टू 0. और एप्सिलॉन एफ से ज्यादा जो एनर्जी लेवल्स होता है दोज आर इक्वल टू 0. ओके, एट टी इक्वल टू 0. So this energy level epsilon f, this is known as the Fermi energy level. All right. And you might ask that why aren't all the particles occupying the energy level zero? Well, the answer is that they are fermions. In fermions, we know that they can, at most one fermion can at a time occupy one level, right? I mean, two fermions cannot occupy the same energy level. They cannot have the same wave function because of their degeneracy. That is why this thing occurs, that every energy level up to epsilon f is completely occupied instead of only one. Okay. So how do we calculate this value of epsilon f from the number density of particles which we are given over here? So हम number density से अब हम epsilon f को निकालेंगे. Okay, at t equal to 0, number density as we know is fixed quantity. So total number of particles is equal to g summation over energy levels j and j, where g is the degeneracy of each energy level as we had seen before. All right, now you had seen that we could express these energy levels in terms of different spherical shells in this K space, right? So previously, when we had derived the energy of a single particle in a box, so then the energy had turned out to be h cross square by 2m kf square k square, where k square was written in terms of kx square plus ky square plus kz square. तो क्या होता है is that we get a sphere in K space, and that sphere corresponds to a certain energy level. And for a different energy level, we get another different spherical shell over here. So similarly, for this Fermi energy level, we have this spherical shell of radius kf. All right. And at t equal to 0, all the energy levels which lie within this spherical shell, that is all the smaller shells, that is entire volume contained within this sphere, gives the total number of energy states that are there. Okay. Right. So that will give me the number density. So since all the particles are present inside all the energy levels which are occupied within this sphere, I can calculate the number density by simply calculating the number of energy states that are there inside the sphere. Or in other words, I only have to calculate the volume of the sphere to find the number density of particles. Okay, so then this summation over j nj is nothing but the volume of this spherical shell. Rho is equal to g multiplied by the volume. Okay, so this is a normalization factor. It does not make much of a difference. You can use any normalization over here. So basically, I have considered a sphere of radius kf by 2 pi. This is the volume of the sphere of radius of kf by 2 pi. So rho is equal to this quantity. Okay. From this, I can calculate kf cube. So rho is equal to g into kf cube divided by 6 pi square. Okay. So then kf becomes equal to 6 pi square rho by g whole to the power 1/3. So kf is nothing but the radius of this Fermi sphere, which I have over here. And from this radius, I can calculate the Fermi energy, which is h cross square by 2m into kf square. So if I put kf square over here, epsilon f turns out to be equal to h cross square by 2m into 6 pi square rho by g whole to the power 2 by 3. तो ये समझ में आया? So this part is clear, right? How I calculate the Fermi energy at zero temperature. Yes.
Yes, sir.
Okay. So basically, I have used the properties of the Fermi gas at zero temperature to calculate the Fermi level. So you might ask, what does this Fermi level depend upon? So one thing is that Fermi level does not depend on temperature. Okay, see, because there is no temperature over here. Fermi level only depends on two quantities. One is the number density of fermions that are present in my gas, and two is the degeneracy. Okay, so these are the only two factors which affect my Fermi level. Now, since in this ground state, every particle occupies every energy state which lies below the Fermi level, and that means that there is only one particular arrangement of particles. So there can't be multiple arrangements of particles because I can only have one particle occupying one level at most, right? So the total number of microstates, that is omega, is equal to 1. Therefore, the entropy of a Fermi gas at zero temperature is equal to zero because log omega is equal to log 1 is equal to zero. Right? So at t equal to zero, S is equal to zero. So a Fermi gas obeys the third law of thermodynamics. That is, at t equal to zero, the entropy of the gas is equal to zero. All right. Now you see that we saw that as t went to 0, beta went to infinity. So the fugacity, that is z is equal to e to the power beta mu, this also goes to infinity, right? Also, in the limit of t going to 0, mu approaches this epsilon f. This we also saw earlier. All right. So now let us calculate this fmz for a Fermi gas. So fm q we had earlier, right? Where we had just put the value of q without substituting q equal to 1. So we substitute q equal to 1, and then fm plus becomes equal to 1 by m minus 1 factorial 0 to infinity integration x to the power m minus 1 e to the power x z minus 1 z to the power minus 1 plus 1. So we had this expression for f. Where was it? E yes, here I think. Uh, right here. So over here, we basically put q equal to 1 and we get f plus. So we define that quantity as f plus. Okay. So here is what f plus is. All right. So what we do is that we multiply the numerator and denominator by m. So m से numerator और denominator को हम multiply किए. So then the denominator becomes 1 by m factorial. And in the numerator, I have a factor of m. So then this is integration 0 to infinity m x to the power m minus 1 e to the power x z power minus 1 plus 1 into dx. Okay, so this is my fm plus. Now I can further simplify this expression over here. तो अगर मैं इस expression को simplify करूँ, then I can write this thing as 1 by m factorial 0 to infinity dx x to the power m into ddx of minus 1 by e to the power x into z power minus 1 plus 1. Okay, so you can write this expression in this manner as well, right? So how do we get this thing? So we get this thing by doing an integration over parts. So if I do an integration over parts, so first I integrate over fx and I get this factor of x to the power m, right? So the term, there is one term which I have put to 0 over here. Why? Because x to the power m multiplied by this quantity, that is 1 by e to the power x z minus 1 plus 1, goes to 0 as x is equal to 0, and also at infinity this thing becomes infinite, so this is equal to 0. So in that way that term becomes equal to 0 and I'm only left with the second term in this integration by parts. So this is the second term which comes out of doing the integration by parts over here. Okay. So let us say that this quantity is something known as h of x. Okay, तो इसको हम h of x बोलते हैं. So h of x is equal to 1 by e to the power x z power minus 1 plus 1. All right. So how does a graph of h of x looks if I plot it as a function of x, where x is the energy, beta into epsilon, right? So at t equal to 0, what happens is that this thing becomes like a step function, which I saw earlier. That is for x less than epsilon f, hx is equal to 1, and x greater than epsilon f, hx is equal to 0. Okay, so x is basically z to the power minus 1 is basically e to the power minus beta mu, which is e to the power minus beta epsilon f. Okay, so for x being greater than beta epsilon f, this quantity is equal to 0 at t equal to 0, and if x is less than beta epsilon f, then this quantity is 1. Now, if I increase the temperature, that means if I lower the value of beta, then you see that this curve deviates from this upper portion, and then it curves like this. And if I further lower the temperature, further increase the temperature, then this becomes even flatter. So you see there is, it deviates larger from the step function and it slowly approaches 0 as x become large. So this curve, this curve, this curve, all these things are drawn at higher values of temperature. So this arrow denotes the direction in which my temperature is being increased. Okay. Now, so since this is what h of x looks like, how would this quantity look like? So minus, this is basically minus of ddx of hx, right? Or minus h prime x. So if I consider a step function and I take its derivative, then it looks like a delta function. Okay. And since the discontinuity is at beta epsilon f, so the Dirac delta function will be peaked at beta epsilon f. So this is corresponding to t equal to 0. And if I further increase temperature, this curve broadens out. Okay, this is for a higher value of temperature, and this is for an even higher value of temperature. So as you see, as I increase the value of temperature, this function minus h prime of x, it broadens out like this. But the common thing about all these curves is that in the low temperature limit, these extreme values, that is very small values of x and very large values of x, this function is equal to 0, right? तो क्या होता है कि जब मैं the common feature among all these curves is that अगर x बहुत छोटा होगा और x बहुत बड़ा होगा तो this derivative जो है इधर ये 0 होता है, ठीक है? So in the limit of t going to 0, you see that this curve is peaked. So on either side of this thing is equal to 0. So this is what I've written over here, that at t equal to 0, h prime is strongly peaked about epsilon f. So, and beyond this peak, it is equal to 0. So we can expand h prime of x about this point, x equal to beta epsilon f in a Taylor series. Okay, or in a power series, since it is very small. So we take this idea into account and then we make the following substitution. What we do is that we can rewrite z power minus 1 into e to the power x in terms of this quantity, e to the power minus ln z plus 1. Okay, so let us denote that t is equal, let t be equal to x minus ln z. So then this quantity is equal to e to the power minus t, right? So at x equal to 0, t is equal to minus ln z, and x equal to infinity, t is equal to infinity. Okay, right. This comes from this expression, x equal to 0, t is minus ln z, x equal to infinity, t is infinity. Okay, so if I substitute this expression into f plus mz, then this becomes equal to 1 by m factorial, which I had over here. X to the power m becomes equal to t plus ln z to the power m. Here x to the power m, t plus ln z to the power m. ddx becomes equal to ddt, right? Because the ln z is basically a constant in this integration over here. So dt is equal to dx. So this is ddt into minus 1 by this thing is e to the power t, e to the power t plus 1. Okay, and the limits of my integration are infinity and minus ln log z. Okay, now we had since this becomes very small, almost equal to 0 at small values of x. At negative values of x, this curve, that is this derivative, this curve is um, equal to 0, right? So that is why almost equal to 0. So basically ddt of this thing is almost equal to 0. So that is why we can, instead of taking the lower limit of as log minus log z, we can take the lower limit as minus infinity only. So if this taking this lower limit at minus infinity does not change the integration because this quantity is 0 in that region only. So basically my integrand is 0 in that region. Okay, so then I replace my log z by infinity. So this becomes integration minus infinity to plus infinity t plus ln z to the power m ddt of this quantity. Okay, now I do a binomial expansion of t plus ln z to the power m. Okay, so if I do a binomial expansion, then t plus ln z to the power m can be written as summation over alpha equal to 0 to infinity mc alpha t to the power alpha ln z to the power of m minus alpha. Right, the normal binomial expansion which we have, where mc alpha is m factorial by m minus alpha factorial into alpha factorial. and m is a fractional value. So m is not an integer over here. So that is why I write this as a summation from 0 to infinity instead of summation from 0 to m. Okay. So if I substitute the binomial expansion into this integral, then fm plus z is equal to summation alpha equal to 0 to infinity ln z to the power of m minus alpha by m minus alpha factorial integration from minus unit plus infinity t to the power alpha ddt of minus 1 by e to the power t plus 1 into dt. Okay, now let us take a look at this quantity over here, this whole quantity. So let s of t be t to the power alpha into ddt of minus 1 by e to the power t plus 1. Okay, so this is nothing but t power alpha e to the power t divided by e to the power t plus 1 whole square. So you see that s of minus t is minus 1 to the power alpha into this thing. All right. So now when alpha is an even function, alpha is even, then s of minus t is equal to s of t, then integrand is non-zero. On the other hand, because um, integration is going from minus to plus infinity, so for minus, negative values of s will have the same values as positive value of x. So this is nothing but 2 into integration from 0 to infinity of this quantity. And if alpha is equal to odd, then s of minus t is equal to minus of s of t. So then this integration becomes equal to 0 because the negative part cancels the positive part. Okay, so that is why we can write fm plus z as summation of alpha equal to 0 to infinity, alpha taking only even values, that is alpha equal to 0, 2, 4, 6, 8, and so on, ln z of m minus alpha to the power m minus alpha by m minus alpha factorial into 2 times integration from 0 to infinity t to the power alpha into ddt of minus 1 by e to the power t plus 1 into dt. Okay, now if I compare with equation 15, so what was equation 15? Equation 15 was this thing. F m plus z is 1 by m factorial 0 to infinity into this thing. So if I compare this expression with this over here, okay. So that was an integral over x and this is an integral over t. That had x to the power m and this one has t to the power alpha. There is alpha factorial outside, there is m factorial outside over here. Okay, and this thing, this is the same thing as what we had got earlier. So this is e to the power t into dt. So basically you will see that this integral, where did it go? Yeah, so this integral is nothing but f alpha plus, instead of m, I have alpha here, f alpha plus of 1. Why 1? Because if you compare with this expression, this is basically what happens if I put z equal to 1. So z equal to 1 gives me 1 minus 1 by e to the power x plus 1. And over here, I have minus 1 by e to the power t plus 1. So z is equal to 1. So this is equal to f alpha plus of 1. So then I can write f m plus of z as ln z to the power of m by m factorial summation m factorial by m minus alpha factorial ln z to the power of minus alpha 2 into f alpha plus of 1 over here. So then now the left hand side becomes easy to evaluate because I can exactly calculate these values of f alpha plus 1 for different values of alpha, right? For example, if alpha is equal to 0, what is f0 plus of 1? F0 plus of 1 is equal to 0 to infinity integration dt into ddt of this thing, which is nothing but because basically this is integration of d of 1 minus 1 divided by e to the power t plus 1. And if I take the limits, this turns out to be equal to half. Similarly, if I have f2 plus of 1, then this is half into integration 0 to infinity to the power 2 ddt of this quantity, which can be further simplified and written in this manner. And if I calculate this integral, this turns out to be equal to pi squared by 12. So in general, you will see that f alpha plus of 1 can be written in a power series like this. 1 minus 2 to the power alpha plus 3 to the power alpha minus 1 by 4 to the power alpha and so on. So for different values of alpha, I will get different values from this power series. And this is a convergence series for all values of alpha. So this exists. I mean, this can be exactly calculated for every alpha going to infinity. Okay, so I have fm plus of z is equal to minus ln z to the power m by m factorial, and then I expand out the summation. I get 1, which comes from the first term of the summation, plus pi squared by 6 m into n minus 1 by ln z square, plus 7 pi to the power 4 by 360 into m minus 1 m minus 2 m minus 3 by ln z to the power 4, plus other higher order terms. Okay, so this is what is known as the Sommerfeld expansion, and this is a very important expression because you see, now I have been able to express fm plus z exactly in terms of, I mean, there is no longer the integral sign, and for any value of m, I can calculate fm plus z by including as many terms as I like. And this is very important if I want to evaluate the statistics of fermions at low temperatures. All right, so how does this help me now? So first, let us look at the number density of these fermions. So I had rho lambda cube by g was equal to f3 by 2 plus of z, right? So I substitute m equal to 3 by 2 over here. So this becomes ln z to the power of 3 by 2. This is 3 by 2 factorial, which is basically gamma 3 by 2. And in the brackets, I have 1 plus pi square by 6, 3 by 2 into 3 by 2 minus 1, that is 3 by 2 into half, which is 3 by 4, into 1 by ln z square, which comes out over here. Plus, also I can calculate for this term also, which I have not done, but if you want, you can do it for this higher term as well. Plus so on and so forth. And it also makes sense to neglect this higher order terms. Why? Because I have t going to 0, that means z goes to infinity. So if z goes to infinity, then ln z, that is log z, also goes to infinity. So 1 by log z goes to 0. So I can neglect the higher order terms because they are of even smaller magnitudes than these ones over here. So up to the simplest order, if I neglect all higher order terms compared to 1, then only this 1 remains. And then what do I get? I get rho lambda cube by g is equal to ln z to the power 3 by 2 by gamma 3 by 2. Okay, that is 3 by 2 factorial, gamma 3 by 2, which is 3 into root pi divided by 4. 4 goes to the top because this is in the bottom. Okay, so now I replace lambda by its expression, that is lambda is equal to h by root over 2 pi m kbt. Okay, kbt is equal to 1 by beta. So then my left hand side becomes this thing. This is equal to the right hand side. So if I rearrange the two sides, then I can express ln z in terms of rho g and beta and h and all these quantities on my left hand side. So I basically take all these things to the left hand side and raise it to the power of 2 by 3. Okay, so then ln z becomes equal to 6 pi square rho by g whole to the power of 2 by 3 beta h cross square divided by 2m. Right. Now you see that this is a familiar thing. So what was my expression for the Fermi energy level? It was h cross square by 2m, 6 pi square rho by g to the power 2/3. So here also I have, what do I have? I have h cross square by 2m, 6 pi square rho by g to the power 2/3. So this is my Fermi energy epsilon f multiplied by beta. So log z is nothing but beta into epsilon f. Right. So this means that log z is beta into epsilon f and z is equal to e to the power beta mu. So this shows that mu is equal to epsilon f. Right. So this was something which we had said earlier, but you see our derivation of f plus and then substitution into this expression also gives us back the same expression. So this shows that our derivation of f plus is correct, and it shows a more rigorous way of calculating the value of chemical potential mu in terms of the Fermi energy. Right. Now, if I retain the next higher order term, then what happens? So what was the next higher order term? Next higher order term was this one, pi square by 8 into 1 by log z square. If I retain the next term, then this is the expression which I have over here. So you see that I already had, I can again take this thing to this side. So this becomes 3 into root over pi by 4 rho lambda cube by g raised to the power of 2 by 3, and this thing becomes 1 plus pi square by this thing raised to the power of minus 2 by 3, because this goes over here, so that's why there is a power of minus 1 into, again, raising to the power of 2 by 3. Okay, so this expression is nothing but the log z which I had got earlier, and this log z was nothing but beta epsilon f, right? So this expression is beta epsilon f. So then log z becomes equal to beta epsilon f into 1 minus pi square by 12 into beta epsilon f whole square. So I can again approximate log, this is the approximation I made. I basically replaced the log z by beta epsilon f over here. Okay, so with this approximation, I can calculate higher order values, a more accurate value of mu. So that means I'm being able to calculate mu at a temperature that is not equal to 0, but at a temperature which is close to 0. Okay, so what is mu at such temperatures? Mu is equal to epsilon f. So beta beta cancel out from the left hand side and the right hand side, and I'm left with mu is equal to epsilon f into 1 minus pi square by 12 kbt by epsilon f whole square plus other higher order terms. So you see that at t equal to 0, mu is equal to epsilon f, right? So this term becomes equal to 0. And when t is greater than 0, then this term is positive, and 1 minus a positive quantity is less than 1. So mu decreases. So this is an important thing, that at finite temperatures, mu is less than what it was at t equal to 0. Okay, and it is a continuously decreasing curve like that. So this is a graph of mu versus temperature. At t equal to 0, mu was equal to epsilon f, the Fermi energy. And as I increase temperature, mu keeps on decreasing, decreasing, decreasing like this. Okay, and then it crosses 0 at some temperature Tf. And we denote this temperature Tf as the Fermi temperature. Okay, so Fermi temperature is something which is for which mu is greater than 0 if temperature is less than the Fermi temperature, and for temperature greater than the Fermi temperature, mu is less than 0. So I can directly read out the Fermi temperature from here, and you will see that the Fermi temperature is of the order of epsilon f by kb. Okay, of the order meaning that it is close to, it fluctuates, it lies around this value. It is not exactly equal to this thing, but it is plus minus a small range of this value. Okay, so Fermi temperature is of the order of Fermi energy divided by the Boltzmann constant. So now that we have learned about these things, we can also do a pressure expansion of uh, fermionic gas at low temperatures. So what do we get if we do the pressure expansion? So beta P was equal to G by lambda cube F5 by 2 plus Z. Okay. And I had the expansion of F here for M. So I basically put M equal to 5 by 2. And then I get G by lambda cube ln Z raised to the power 5 by 2 divided by 5 by 2 factorial. 5 by 2 factorial is equal to gamma 7 by 2. Okay. Multiplied by 1 plus I place M equal to 5 by 2 here. So it is 5 by 2 into 3 by 2, which is basically a 15 by 4. 15 by 4 divided by 6 becomes a 24, and so on. And if I calculate this thing, then becomes equal to 5 pi square by 8, 1 by ln z square. Okay. So then g by lambda cube. So then the left hand side, that is beta p, is equal to g by lambda cube into 8 by 15. Basically, gamma 7 by 2 is equal to 15 by 8 into root pi. So this becomes 8 by 15. ln z to the power 5 by 2 divided by root pi. 1 plus 5 pi square by 8 into 1 by ln z square, and so on. Okay. So now in the previous section, we saw that ln z was equal to beta epsilon f minus pi square by 12 into beta epsilon f whole square. So what we do is that we replace that over here. So if I replace that, then it becomes 8 by 15 g by lambda cube 1 by root pi beta epsilon f to the power 5 by 2 into 1 minus pi square by 12 into beta epsilon f whole square plus higher order terms. This entire thing raised to the power 5 by 2. multiplied by this quantity over here, 1 plus 5 pi square by NZ. Okay, so what do we do next? Um, I can directly read off the expression of rho, because rho, as we saw earlier, was rho lambda cube by g was equal to this thing. Rho lambda cube by g was ln z to the power 3 by 2 by root pi into 4 by 3. Okay, so you will see that this quantity is nothing but rho multiplied by 2.5 2 by 5 into beta epsilon. And then we do a binomial expansion and we retain only the first order term. So 1 minus 5 pi square divided by 24 beta epsilon square plus this quantity. Okay, so then I multiply these two quantities and only retain those terms which are which are of the order of t square, and I neglect all the terms which are of order of t to the power 4 and higher order terms. Okay, because basically I'm working at a temperature which is much less than the Fermi temperature. Okay, in that limit, I can neglect the higher order terms. So what do I get? I get beta and beta cancel out from the left hand side and the right hand side. So P is equal to rho into 2 by 5 into epsilon f multiplied by 1. And then if you multiply this quantity, you have 5 pi square by 8 minus 5 pi square by 24. So that becomes plus 5 pi square by 12 into 1 by beta epsilon f whole square, and 1 by beta epsilon f whole square is nothing but kbt by epsilon f whole square, plus other higher order terms which are negligible when kbt is much less than epsilon f. Okay, so an important thing which you can see from this expression over here, equation 24, is that even at t equal to 0, pressure is non-zero, right? Because at t equal to 0, the energy, that is epsilon f, it is non-zero quantity, right? So at t equal to 0, pressure is non-zero. So this is how it is completely different from a classical ideal gas. So in a classical ideal gas, you had at t equal to 0, the equation of state was PV is equal to nkbt, right? So at t equal to 0, you had P equal to 0 if the volume was constant. On the other hand, for ionic gas, this is not the case. P is non-zero. P is equal to, in fact, 2 by 5 rho into epsilon f at t equal to 0. And this is what we know as the Fermi pressure. And this is also known as the degeneracy pressure. And this is an important quantity. Why? How is it important in physical systems? Where one system where this is important is a neutron star. So neutrons, as you know, are fermionic particles, right? So this degeneracy pressure, it has plays an important role in determining the collapse of a neutron star. Okay, so as you know, a star has a very large mass, and because of the large mass, it has a very large self-gravity. That is, there is a gravitational attraction which pulls all the mass towards its center. So in the absence of anything, any other thing, it should collapse under its own weight, right? But there is a constant nuclear reaction inside the sun, inside any star, which basically powers that star. Okay, that's why the star is shining, because of the nuclear reaction which happens inside the sun, inside that star. And because of this shining nuclear reaction, there is radiation which comes out of the star, which leads to some sort of a pressure, which is known as the radiation pressure. So this radiation pressure acts outwards against the gravity of the star itself, and so because it acts against the gravity, it sort of prevents the collapse of the star against gravity. And this is not the only thing. You would see that there is another pressure that is acting inside the star, a neutron star. Okay, this was for a normal star, which I said, but for a neutron star, there is an additional pressure other than the radiation pressure. And that is this pressure, okay? This degeneracy pressure or the Fermi pressure. So the degeneracy pressure also prevents the gravitational collapse of a neutron star. So the degeneracy pressure plus the radiation pressure leads to a total outward pressure which acts against the self-gravity of a neutron star, and this is what prevents its collapse. So this is also what is known as, what is sort of used in the derivation of this Chandrasekhar limit of white dwarf stars. So Chandrasekhar limit actually sets a limit on the mass of the stars. So below that uh, limit, you cannot have a white dwarf star. So that limit is basically set by this degeneracy pressure value. So that is the important implication of this degeneration pressure in astrophysical systems like neutron stars. And there are also other systems where this is applicable. Okay, so now that we know about this degeneracy pressure, we can also calculate the internal energy from this formula, that is 2 by 3 into P is equal to U. So basically, if I multiply this by 2 by 3, sorry, yeah, yes, U is equal to basically, sorry, P is equal to 2 by 3 U. So U is equal to 3 by 2 into P. Okay, so this is 3 by 2 into P. And so then if I multiply this by 3 by 2, this becomes 3 by 5 rho kBTF into 1 plus this entire quantity. So this is the internal energy of a Fermi gas at low temperatures. And again, at T equal to 0, internal energy is non-zero because of the exclusion principle that all the energy levels up to epsilon F are completely occupied. Okay, so if I put T equal to 0, I can get the energy of the Fermi gas from this expression. And as you see, the energy depends on two things. One is the Fermi energy level, epsilon F, and the other is the density. And we saw earlier that the Fermi energy level also depends on two quantities, density and degeneracy. So all these things, the Fermi pressure, the internal energy of a Fermi gas at T equal to 0, all these quantities, they only depend on two things, that is the density of the Fermi gas and the degeneracy of the Fermi gas. Okay, so now that we have this internal energy, I can now calculate the specific heat at constant volume, right? So specific heat at constant volume per unit volume, that is CV by CV, CV by V, is equal to d small u by dt. Okay, and u was over here. So if I take the derivative of this expression, so first term is equal to 0 because there is no dependence on temperature. The first dependence on temperature comes from the second term. So this becomes pi square into rho kb by 2 into T by Tf plus other higher terms which are of the order of T square and so on. All right. So then if I multiply this by the total volume, then I can get the specific heat capacity of the Fermi gas at low temperatures. So if I multiply this side by volume, so rho into V becomes equal to capital N. So CV is equal to pi square by 2 NKB into T by TF plus terms which are of the order of T by TF square and so on. So an important thing to notice is that in ideal gas, what we saw was that CV was a constant. Why? Because the internal energy, it was linearly proportional to temperature. So du by dt ended up being a constant equal to 3 by 2 nkb. Okay, and here for Fermi gas, it increases linearly with temperature at low temperature. And as I go up to higher and higher temperature, it slowly approaches the ideal gas limit. So this is the limit T equal to infinity, where this is the ideal gas value. And this is a specific heat of Fermi gas. Okay, so this is CV for a Fermi gas. At very small values of T, I can neglect these terms and then I can approximate this with this linear curve. Okay, so you see this linear curve, which is a tangent to this curve at very small values of T. And at higher temperature, this curve deviates from this linear variation. And at very high temperature, the specific heat approaches the ideal gas value. Okay, so this is a generic property of all Fermi gases. That is for sure. Okay. So instead of doing this very rigorous derivation of specific heat, I can also understand this from a more simplistic perspective, like a more physical way. So till this part, is everything clear, or are there any questions? Are there any questions or comments, doubts? Okay. So let us see how we can understand the variation of specific heat from a more physical perspective instead of going through all these large derivations. So we see that when temperature is very small but non-zero, then what happens? So at T equal to 0, the average occupation number of energy levels, it followed this step-like function where all energy levels below the Fermi energy were completely occupied. All the energy levels above Fermi energy have zero occupancy. Okay. So at finite temperatures, we saw that there is a finite occupation of levels below the Fermi energy and finite occupation of levels above the Fermi energy, right? So that is why the average occupation number for T greater than 0, it scales like this. Okay. So what are the energy levels which are occupied at values of temperature which are slightly greater than 0? So you see that it is like, like you have a valence band and a conduction band. You excite electron, it goes from a valence band to a conduction band. It leaves a hole in the valence band and goes over to the conduction band, right? So when you apply a current across a semiconductor. So here also the concept is pretty much similar. So when you excite the gas at T equal to 0 by raising the temperature, then the energy levels which get excited are those energy levels which are only slightly greater than the Fermi energy level, right? So a few particles from these energy levels occupy this energy level. That is why the occupancy of these energy levels increases, while the occupancy of the energy levels which are lower than the Fermi energy level, it decreases, right? So particles travel from this energy level to this energy level as you increase temperature. And this excitation first takes place at uh, across an energy difference which lies around this, which is lies in the neighboring neighborhood of this Fermi energy. And then as I increase the temperature, other energy levels which lie at energies much lower than the Fermi level get excited. Okay. And so this curve spreads out even more and more. So let us look at the limit when T is only slightly greater than 0 and only a small number of energy levels above the Fermi energy are excited. Okay, so then the number of energy levels which are excited are basically the number of excited levels in a shell of thickness delta K above the Fermi wave number. So earlier we saw that we can express the energy levels in terms of this spherical shell, right? So here is the sphere of Fermi wave number, and all the shells which are lying within this sphere are the occupied levels. So as I increase the temperature, there are some energy levels which are beyond this sphere which get excited. And so the number of excited levels is basically a spherical shell whose thickness is a very small value, which is delta K, which is greater about this K equal to Kf. Okay. So basically, the number of energy levels is the number of spherical shells which lie within a thickness delta K above the Fermi wave number Kf. And what is the volume of this spherical shell? The volume of the spherical shell is basically 4 pi into Kf square multiplied by delta K. Right. It's like the volume of a very thin spherical shell, which you can calculate from geometry. Okay. So we know that Ek, that is the energy of the kth level, is h cross square by k square by 2m. Then the occupation probability of the kth level is basically 1 by e to the power beta into epsilon minus epsilon f plus 1, basically the Fermi Dirac distribution function. Okay, so now in this limit that t goes to 0, this is a large quantity, and we consider those levels epsilon which are greater than epsilon f. So this is a positive quantity and a large quantity. So basically e to the power beta into epsilon minus epsilon f plus 1 is equal to, we drop the minus 1 from here, and therefore nk becomes equal to e to the power minus beta epsilon minus epsilon f, where epsilon is only slightly greater than epsilon f. So using this formula, I can write this as exponential minus beta h cross square by 2m k square minus kf square. Okay, where k is greater than kf. Now k square minus kf square. Sorry, this is not whole square. This is k square minus kf square can be written as k plus kf into k minus kf, a square minus b square formula. And since k is almost the same as kf, this is approximately equal to 2kf. And this is my delta k, which is k minus kf. Okay, that is the width of this spherical shell which is excited. So k square minus kf square is equal to 2kf into delta k. And I substitute this into this expression. So nk is equal to exponential minus beta h cross square by 2m into 2 times kf into delta k. So this is e to the power minus beta h cross square by m kf times delta k. So these are the number of particles which occupy the higher excited level k, which is only slightly greater than kf. So now for nk to be a finite quantity, what is required? So you see that if delta k is very small, then e to the this is basically e to the power of right. So if this beta is a very large quantity, okay, beta is large quantity meaning that this is minus of a large quantity. Okay, so in order to manage that, delta k needs to be of the order of m by beta h cross square into kf. Right. If delta k is of the order of m by beta h cross square kf, then only there will be a finite number of excited levels. If delta k is less than this quantity, then there will be zero, zero energy levels basically which are excited. Okay. So these are, and this is what a delta k needs to be for there to be a finite number of excited energy levels. In that case, the fraction of excited energy levels will be 4 pi kf square into delta k. I replace the delta k which I got over here into this expression. So 4 pi kf square into m by beta h cross square into kf. And this thing I multiply by 1 by the volume of the Fermi energy sphere. Okay, 1 by the volume of the Fermi sphere. That is 4 pi by 3 into kf cube. So this gives me the fraction of the levels that are excited. That is the number of excited levels divided by the total number of excited levels. And this thing you will see, this is nothing but kBt by kf square. And kf square was of the order of epsilon f, right? Because epsilon f is equal to h cross square kf square by 2m and so on. So this is basically kBt by epsilon f. And epsilon f is equal to kb into tf. So this is of the order of t by tf, where tf is the Fermi temperature. So this gives me the fraction of the excited energy levels. So the number of fermions that are excited are basically the total number of fermions multiplied by this fraction. So this is n into t by tf. So then the change in the internal energy of the system is given by delta U, which is the number of excited fermions multiplied by the kBt. That is basically the multiplied by the unit of energy associated with each fermion. That is Ne into kBt. So this becomes n kBt square by Tf. So this is delta U. So my specific heat is basically delta U by delta T. So if I take a derivative of this with respect to T, then it becomes of the order of T. So you see that Cv is linearly proportional to T. Okay, so this is another way of more physical way of saying that how that at low temperatures, the specific heat is proportional to the temperature itself. Okay, so are there any questions up to now? Okay, so if there are okay, so if there are no questions, then let us see what happens to a Bose gas at low temperatures. This is even more interesting. Okay, so for bosons, we know that the average occupation number of the jth energy level, that is Nj, is equal to G by e to the power beta into epsilon j minus mu minus 1. Right. And we know that this average occupation number can never be negative. This is always greater than or equal to 0. Okay. Now, one difference between bosons and fermions is that there is no restriction on the number of boson that can occupy a particular energy level. Right. So that means that for fermions at t equal to 0, we saw that there could be one fermion in each energy level. And depending upon the total number of fermions that were there in the system, they could all populate the energy levels up to the Fermi energy, right? Which depended on the total number of fermions that are there in the system. So for bosons, what we expect at t equal to 0 is that all of these bosons will occupy the lowest energy state. And the energy is given by h cross square k square by 2m. So the lowest energy state corresponds to this ek equal to 0, that is k equal to 0. So at t equal to 0, we would expect that all the bosons will occupy the state corresponding to k equal to 0. right? So that will be the state with my lowest energy. Okay, so what happens in that case? So since nj is always greater than 0, so this means that this thing should always be greater than 1, right? So if this thing is greater than 1, so this means that epsilon j should be greater than mu, right? Because if epsilon j is less than mu, then this thing becomes less than 1 and nj becomes negative. Okay. So the constant is that epsilon j should always be greater than mu for all values of j or k over here. Okay. And we know that the lowest value epsilon j can take is equal to 0. So this means that 0 should always be greater than mu. Or in other words, mu should always be less than or equal to 0 for bosons. So this is an important aspect of bosons, okay, that the chemical potential of bosons is always less than or equal to 0. At t equal to 0, the chemical potential is 0. This can be directly seen, which I will also, which you can see right now, which I will be showing you. And at higher temperature, it is much more negative. So for fermions, we saw that the chemical potential was positive at t equal to 0. It was equal to the Fermi energy level. It went to 0 at t equal to Tf, and below that it was negative. For bosons, it is always negative. And it is equal to 0 at t equal to 0. Now, how does that come about? Well, z is equal to e to the power beta mu. So mu is equal to kBt into ln z. Right. So in the limit of t going to 0, what do I have? So basically, because mu goes to 0, so from this expression, right? Right. So from this expression, you see that at t equal to 0, mu is equal to 0, right? And as t goes to infinity, what happens over here as t goes to infinity? So this becomes log of 0, and log of 0 is minus infinity, right? So that is why mu becomes minus infinity on raising the temperature. So that is why the graph of mu looks like this. It starts from 0 and goes up to minus infinity at high temperatures for bosons. So the range of values that mu can take are between minus infinity and 0. And corresponding to this range, the values which z can occupy are 0 to 1. So mu equal to minus infinity corresponds to z equal to 0, and mu equal to 0 corresponds to z equal to 1. All right. So basically, the zero temperature limit of a Bose gas corresponds to the limit z approaching 1. Okay. So we have to look at the statistics of Fm. Now I put a minus sign over here because Q is equal to minus 1 for bosons. You have to look at this quantity Fm minus Z in the limit of Z going to 1. Okay, so as t goes to 0, mu goes to 0 and Z equals goes to 1. And now I study this quantity 1 by m minus 1 factorial, this thing in the limit of Z going to 1. So the first thing that I'll see is that this quantity is monotonically increasing in the limit of 0 less than z less than 1. How is it monotonically increasing? Well, here's the proof. Let us consider some value z which is greater than z prime. Okay, so then minus z prime is greater than minus z. E to the power minus e to the power x minus z is less than e to the power x minus z prime, right? I take the reciprocal of these two sides, so this sign gets interchanged. So 1 by e to the power x minus z is greater than 1 by e to the power x minus z prime. Then I multiply the numerator and over here by z, and this one by z prime. So since my z was greater than z prime, so z by e to the power x minus z will always be greater than z prime by e to the power x minus z prime. I divide this one by both numerator and denominator by z over here, and I divide the numerator and denominator by z prime. So 1 by z inverse e to the power x minus 1 is greater than 1 by z prime inverse e to the power x minus 1. This quantity is nothing but this one, right? So this implies that fm minus z is greater than fm minus of z prime when z is greater than z prime. Or in other words, fm minus z is monotonically increasing in this interval of z. Okay, so this part is clear then. So we see that since z is constrained between 0 and 1, the maximum value which fm can take occurs at z equal to 1. So fm minus reaches its maximum value at z equal to 1, and this maximum value is fm minus of 1, which is 1 by m minus 1 factorial, 0 to infinity x to the power m minus 1 divided by e to the power x minus 1 dx. Okay, now since we have t going to infinity, we consider the we have um, as x goes to 0, we see that the integrand is finite only when m is greater than 1. All right, so if m is less than 1, then you will see that this integrand blows up as x goes to 0 and this integral does not exist. So basically fm minus 1 diverges when m is greater than 1. Okay, so this is another characteristic of this quantity. We can also take a look at the derivatives of fm minus. Okay, so I take the derivative with respect to z, 1 by m minus 1 factorial 0 to infinity x to the power m minus 1 ddz of this quantity. Now I can write the ddz of this quantity in terms of its derivative with respect to x. How do I do that? I define g as 1 by z inverse e to the power x minus 1. Okay, then dg by dz is equal to dg by dz inverse e to the power x into d of z inverse e to the power x by dz. This is basically the chain rule. I can further break this up. So I again apply chain rule over here. So this is dg by dx, dx by dz minus 1 e to the power x into this quantity dz minus 1 e to the power x by dz. Okay, so if I take this derivative first, that is derivative of z power minus 1 e to the power x with respect to x. This is e to the power x into z to the power minus 1. Okay, and the derivative of this term with respect to z is basically minus z to the power minus 2 e to the power x multiplied by dg in dg dx. So this is nothing but minus 1 by z dg dx. So I replace this expression over here in place of ddz. So the left hand side, that is t dz of fm minus of z, is becomes minus 1 by z into 1 by m minus 1 factorial integration 0 to infinity x to the power m minus 1 ddx 1 by z to the power minus 1 e to the power x minus 1 into dx. Okay, now I do integration by parts. For integration by parts, first I integrate this x to the power, first I integrate this term, this ddx term. So that's how I get the first term. And you see that this is equal to 0 at both x equal to 0 and x equal to infinity. And then I take the derivative of x to the power m minus 1 and I get the second term. So then d fm minus of z by dz is equal to 1 by z, 1 by m minus 2 factorial integration from 0 to infinity x to the power m minus 2 by z inverse e to the power x minus 1 into dx. Okay, and this you see is nothing but f of m minus 1, right? So d of fm dz is equal to 1 by z f of m minus 1 for bosons. Okay, so we had seen in this expression that if m is greater than 1, then only this integral exists. Otherwise, it diverges for m less than 1. So if m minus 1 is less than 1 or m is less than 2, then the derivative diverges at z equal to 1. Okay, so this is the condition on the derivative and so on. So now let us see what this implies for the number density of the particles at low temperatures. So we saw that rho lambda cube by g was f3 by 2 at offset. So here it is for bosons. That's why I put the minus sign. Now in the limit of t going to 0, we have as z approaches 1, this will be infinity, sorry, this will be 1. So when z approaches 1, so rho lambda cube by g is equal to f3 by 2 minus of 1, which is equal to, so this quantity f3 by 2 is nothing but 1 by gamma 3 by 2 integration from 0 to infinity x to the power half e to the power x minus 1. So basically I've put z equal to 1 in this expression. Now this integral is nothing but gamma 3 by 2 into zeta 3 by 2, where zeta is basically the Riemann zeta function. The Riemann zeta function zeta of x can be written in terms of a power series like this. So zeta of x is equal to summation n equal to 1 to infinity 1 by n to the power x. which is 1 plus 1 by 2 to the power x plus 1 by 3 to the power x plus 1 by 4 to the power x and so on. So the Riemann zeta function can also be expressed in terms of an integral like this. So you see that the left hand side, which is rho lambda cube by g, becomes equal to nothing but the Riemann zeta function, which is zeta of 3 by 2, which is equal to 2.612. So this is a very interesting thing to note over here. So you see this value of Riemann zeta which I got was the largest possible value of f3 by 2, right? Because z is always constrained between 0 and 1. So in some sense, this is giving me the largest number of excited state I can have at a given temperature. Okay, so this is basically like an upper bound on the density of the excited states. So if I denote rho star as the density of the excited states, then rho star into lambda cube by g is always less than or equal to zeta 3 by 2. Okay, this is like an upper bound on the density of the excited states. So at high temperatures, when temperature is very high, you will see that lambda cube is a small quantity. So this inequality is automatically satisfied. That is rho star into lambda cube by g is less than zeta 3 by 2 always. Or in other words, number density into lambda cube by g is always less than this quantity. So this inequality is satisfied at high temperatures. So at high temperatures, basically we can have all the energy levels to be excited at high temperatures. Okay. Now the tricky part happens when temperature is low. So at low temperatures, you will see that lambda cubes gradually becomes larger and larger for a given value of rho. So if I hold rho fixed and I increase lambda, then you will see that this inequality is not satisfied beyond the particular value of temperature. Okay, and this value of temperature beyond which this inequality is not satisfied is known as a critical temperature. Critical temperature for what? Critical temperature for Bose-Einstein condensation. Why do I call this a condensation now? That is the important question. So you see that beyond this critical temperature, what happens is that out of all the energy levels which are there, some of the energy levels, I mean, there is a maximum number of energy levels which can get excited, right? So the maximum number of energy levels that can get excited is less than the total number of particles which are there in the system. Right. So what happens to all the other particles? All the other particles, they go on to occupy the zero energy level when the temperature is lower than the critical temperature. Okay. And this macroscopic occupation of this zero temperature level by all the other particles which are there, which are the non-excited particles, this phenomenon is known as Bose-Einstein condensation. And this formation of this large occupancy, this state is known as a Bose-Einstein condensate. Okay, so this is sort of like a phase transition which occurs at this critical temperature of T equal to Tc. And how do I calculate the critical temperature? I basically calculate the critical temperature from this expression over here. That rho lambda cube by G is equal to zeta of 3 by 2. So I can express lambda cube in terms of my temperature. All right. So I basically replace lambda by lambda C. C stands for criticality. This is equal to zeta 3 by 2. So then Tc is equal to h square by 2 pi mkb into rho by g zeta to the zeta 3 by 2 whole to the power 2 by 3. So this is the critical temperature for my Bose-Einstein condensation. So you see that in case of fermions, there was no such condensation which took place. Like there was no, by condensation here, I mean a large occupancy of a single energy level. Okay. So in case of fermions, such large occupancy of the single energy level never occurred, because there was the constraint that one fermion can at most occupy one energy level, right? But here there is no such constraint. So you see that as soon as the temperature of the Bose gas goes below the critical temperature, then this condensate forms. And that is a macroscopic occupation of this low energy level. That is the lowest energy level. Okay. And for a given Bose gas, the critical temperature depends on a few factors. What are the factors? The most important factor is the density of the gas. You see that for a more dense gas, the critical temperature is higher. That means it is easier to form a condensation at easier to obtain a condensation if the gas has a higher temperature, higher density. Sorry. Okay. So for a higher gas density, the critical temperature for Bose-Einstein condensation is higher. It also depends upon the degeneracy of the gas. That is where the quantum effect comes into this critical temperature. It is not a classical thing, it is a quantum thing, and this quantum thing comes in from the degeneracy of the gas. Okay. It also depends upon the mass of the particles which forms the gas. So this is what I had explained earlier. So when my temperature is greater than the critical temperature, then there is no Bose-Einstein condensation and all my energy levels are excited. So the number of excited energy states is basically equal to the number density of the particles. And when the all the particles are excited basically. And when temperature is less than the critical temperature, then the number density of excited particles is constrained by this value. So at T less than Tc, number density of excited particles is given by G into zeta cube by lambda C cube. And from this also, and this depends on the critical temperature. So this goes hand in hand. The number density of particles at excited particles at a temperature less than Tc, it solely depends upon Tc. Okay, it is not depending on what the temperature is. It only depends on the critical temperature, and that is a constant. That is why all the other particles which are there, they go on to occupy the lower energy state. So the density of the condensate at T less than Tc is given by rho minus rho star, which is rho minus this quantity. So this gives me the density of the condensate. And as you can see, if I have a more dense gas, then my condensate, which occurs at T less than Tc, will also be more dense because rho will be larger for that. Okay. So this is what Bose-Einstein condensation basically is, and it can also be expressed in terms of this graph over here. That is, with increasing temperature, this is my total density of particles, which is always a constant. This is the number density of the excited particles, which you see increases, and then it hits the maximum value, and then it stays a constant like this. Okay, for all temperatures. So basically, once it becomes equal to the total density of the gas, it becomes constant. And this is the number density of the particles which form the condensate. So such that this variation is such that the total density is remains a constant. That is rho star plus rho zero is always equal to rho. So as my temperature decreases, the density of the condensate increases, the density of the excited particles decreases, and at zero temperatures, all the particles occupy the zero energy levels and there are no particles which are excited. Okay. So this was all about Bose-Einstein condensation and the low temperature statistics of Fermi gas and the Bose gas. So that was all that I had for today. So are there any questions or doubts regarding whatever that has been covered today? Any doubts or questions?
No doubt, sir.
Okay. So in the next class, then I will discuss a few problems about Bose-Einstein condensation, basically the real world applications such things have. Okay. So that is what I will discuss in the next class. And probably you will also, I mean, these things like Chandrasekhar limit and the statistics of neutron stars and black holes and all these things, I think they will also be covered in the course. Okay. So you can go through that as well. So next week I will be discussing a few problems based on this. So yeah, so that is it. So yeah, thank you for joining today and I will again see you next week. Okay.
Thank you, sir.
Okay. Bye.